Oh, I'm back. Oh, now I'm too friggin' short. One moment, please. All right. I'm still a little short. Alrighty. So we're left off as a parallel circuit. So you notice we have coming out of the battery, we have lots of current, and it divides into one path and another path and another path. So this is going to be the law of conservation of charge when we talk about the Kirchhoff rules, which is the junction rule. That any current coming out of the battery has to be coming back in, or any current going through this bulb has to be coming back out of the bulb, because we don't have any charge being eaten up, destroyed, or created anywhere. It's just coming in and it's coming right back out. So whatever comes into the junction is also leaving the junction. Okay? So in parallel, what's the same in parallel? It's the potential is the same. Because if this is a plus 6 on this side, that's a plus 6, plus 6, plus 6. Then it drops to 0 on the other side. So the potential is the same everywhere in this series, but the current is not. So you have to add up this path, plus the blue path, plus the red path. They all add up to be the total current. Okay? So it gets a little crazy when you get to how to add the resistors in parallel because, let me go back one. Pretend if we only have just one light bulb. Is it any harder to go through this light bulb if we have two more paths? It's not any harder. It actually makes it easier because rather than one little skinny filament, you have two little skinny filaments side by side. That's twice the area. That makes it easier to flow. The resistance actually drops. And if you have three of these, that's 3 times the area you could be going through. That has to be 1/3 the resistance. So resistance actually drops in parallel. It just makes it easier. So that's to find the resistance in parallel. You got to do 1 over the 1 over 1 over, and then you got to inverse this, flip this over when you finally sum up and solve for the final R. Okay, so potential is the same everywhere. Current is not. You got to sum them all up. Okay. All right. Well, here we go. So a little practice. You got a 5, 7, and 9. So first thing I look at is I know, well, if I don't have a 7 and 9, my resistance is 5. When I add a 7 and a 9, it's not going to be more resistance than 5. It's just going to make it a little bit easier because I have more paths to go. So my total resistance will be less than 5. So you do 1 over 5 plus 1 over 7 plus 1 over 9. You could do a common denominator thing, or you could just use your calculator, and it's 0.454. But remember, when solving for this, that's not your resistance. That's 1 over the resistance. You got to invert that. So you go 1 divided by the 0.454, and that is equal to 2.2 ohms. And it's less than what we talked about before. Okay, so it works. The resistance, total resistance actually drops below the 5. It's always going to, in a parallel circuit, it's always going to be less than the smallest resistor. Okay, so to find the total current, well, if your total voltage is 8 and your total resistance is 2, well, that's kind of going, all you do is just your I time to find what the current is. It's just the 8 divided by your 2.20, and that's your 3.64. That means you have 3.64 amps positive current coming out, and it branches off. Hey, pop quiz, which one of these three is going to have the greatest current and why? It's not the 9, it's the hardest to go through, it's the 5. So the 5 will have the greater current, the 9 will have the least amount of current because it's harder to go through. Okay, but remember you have the same potential difference across every one of these. A plus 8 here, and it's a 0 on this side. Or you can think of this as a 0, and this is a minus 8. There's still a difference of 8 volts. You can think of this as a plus 4 on this side, and this is a minus 4. If this is a plus 4 and this is a minus 4, so the difference is still 8. So to make it easy, we call that a plus 8. We call that a 0. Okay, so the voltage drop is 8 across each one of those. Now to find the current, you just do an Ohm's law across each one of those. So you 8 divided by the 5, 8 divided by the 7, 8 divided by the 9, and shabam, this is, I said earlier, the most current goes through the least resistance. Okay, and if I go 1.6 plus 1.14 plus 0.9, Dios mio, what does that equal to? 3.64, the same as the total. Law of conservation of charge. Okay, alrighty. So, talking about the current law here. So in this case, you don't really have to use Kirchhoff's laws when you have a single battery. We just have a simple parallel setup. You don't really have to do this, or you do it without even thinking. Where you want to use Kirchhoff stuff is when you have more than one battery. Then it gets a little tricky. But that's a whole separate PowerPoint altogether. Okay, so what we do here is in parallel, we tend to define the total current. We make this into a single resistor. And we do that by doing the 1 over the R, the 1 over the R thing. Okay, so in this case, we've got a 20 volt thing, and now we're looking at loops here. Oh, here's an example of Kirchhoff's law with 2 batteries. So this gets tricky trying to figure this out just using Ohm's law to find what the total flow is. But this is where Kirchhoff makes this a pretty easy thing to do. So this is one loop of current going this way, and then we have another battery that has another loop going this way. And you could actually predict the wrong direction, and that's fine. It doesn't matter if you get it backwards. You just have to remember to do things, make things either negative or positive, and it still works out to be the same answer, even if you have the current going the wrong direction. You'll know it because you'll find a negative current somewhere. That just means you picked the wrong direction. Okay? So what happens is in these 2 loops, this is a plus 24. By the time you drop here and here, you're going to be down to 0. This is a plus 12. By the time you drop over the 2 and drop over the 6, that's going to be a 12 volt drop as you get back over there. So you have 2 different equations to work with. We have the current here, I1, and then you got current I2, and then you have a current I3 going in this direction, the combo. Now notice using our joint rule before, which is 2 things in Kirchhoff, the law of conservation of energy, which is the loop rule, and then the junction rule, which is the joint rule that I was just talking about. That whatever current comes in, it has to be going out. So this I1 plus I2 has to equal I3. So that's one of our equations we set up. We set up that equation, we set up the potential one for the blue loop, we set it up for the red. Now we have 3 equations. And we have, at this time, we don't know any amounts of current. We have 3 unknowns. Well, we start substituting. You start substituting one in for the other, and then you get it down, and you're working with these equations, and you finally get it down to what the unknown is. More practice on that on another day. So this is kind of talking about how, okay, solving it down for the 3, then we substitute the 3 in for that one, and then we have another unknown here. We substitute that in for that one, and by the time you set it looks messy. It does look messy. It does take a little practice. Then you finally get that down to your final answer, and hey, that's a negative 0.545 amps. How does that a negative? All that means is they got the direction of the loop wrong. The current's actually going in this direction. Okay, that's why right there it's a negative. Then if you want to find the other current, you just pop that in your equation, solve for the other currents in other spots, tell you exactly what the current flow is. But we're going to do more practice on that on a whole different other day. Just means you're going to go in the wrong direction. Not a big deal. Alrighty. And then this talks about how to go back and solve for the I1. You just plug in those numbers back in for the other ones, and you finally go back through and you find all the other little answers to all of those gems. Alrighty. Now back to the 1 battery thing. It's a lot easier with 1 battery. You don't have to do all the Kirchhoff stuff. So you got a combo circuit. What do you do with the combo? You make this parallel into a series. So 1 over 100 plus 1 over 50, and then you invert that. When you add those together, you get a 33. Now you have 2 in a series, you add those together, and there's your total resistance. Okay? So when you have a compound, which for the 3rd circuit, that's what you're going to do on your practice stuff, on your FET. You're going to have different bulbs, different resistances, and if you don't understand now, when you do the FET, you can actually click on the bulbs. It'll tell you what the resistance of the bulbs are in the FET, and you can actually change the resistance. You have a different resistance of bulb. But the point is, when you have a compound, you make it into the same kind of circuit. In this case, you do it a series. If this one was over here, I would make these 2 in a series into 1 resistor, then I'd have 2 in a parallel. Okay, so it just depends on how they're combined together. And there you go. There's how you find your total resistance that we just talked about. Alrighty. So now that we have that resistance and the total resistance, you know the potential, if it's given as 120, what's the total flow of current? Now you just plug it and chug it. So you got a 1.06 amps flowing through here. Now you can find your voltage drop. Now that you know the total, because all the current goes through this one, it splits here and here. Twice as much current goes here as here. So 2/3 go here, 1/3 here, because it's twice as easy to go through. Okay? So to find the voltage drop across the thing, it's just your total current times the 80. That's your 84.8. You might think, hey, what's the voltage drop across here, which is the same for both of them? Well, it's your 84.8 minus the 120. Whoops, I maybe did that a little quick. Or, you know what, this resistance is 33, you use the same thing. If this is a single one of 33, you know it's 1.06, you do the same thing, 1.06 times your 33, and you get the voltage drop across there as well. The second way to do it, okay? So that's kind of what this is talking about. You take your total 120 to minus the 84. Remember, it's 84.8 drop across here, and that's how you could solve for that voltage drop across here. So there's a lot of ways to do that stuff. Okay, and then to go back in the current, define the currents, they split up and they add back together to be the total right over there. Okay, so you know the voltage drop across each one of these is 35.2 divided by the 100. That's 0.3, whatever. And that's a 0.7. You add those two together. What do you get? Hey, you get 1.06, the same as the total. Alrighty, and it adds up to 1.06. Bam! Hey, that's it. And I have 4 minutes to spare. What do you want to do with this last 4 minutes? Anything? All right. We'll get to work on your lab then. All right. Hasta luego.